Okay. Assalamu alaikum. My name is Baher Elsheikh. I am a staff mechanical engineer in SABIC Agri-Nutrients. It's one of SABIC affiliates. Today you will have a presentation about how to prevent failures in shell and tube heat exchangers. In our slides today, actually we will pass by first an introduction about the heat exchangers and how it can be classified, and then we will see how across the life cycle of the heat exchanger we can maintain the mechanical integrity and avoid failures and process safety issues. At the end, we will have some 3 to 4 historical cases explaining at which stage of heat exchanger during design, during fabrication, and during operation also, and the maintenance and inspection, how we can keep and maintain the heat exchangers. The heat exchanger or shell and tube heat exchanger, one of the most common equipment used in oil and gas industry and in petrochemical and also in the power and energy section. And its impact is quite major because of the popularity and how it is used in the plants. It can be classified based on its function, either to be normal heat exchanger, cooler, heater, or condenser, reboiler. You can see it in many locations based on how the function required, whether it is to heat or to cool. From the first glance, when you see the exchanger, you can feel why it is quite special compared to the normal pressure vessels. You can see that it is quite complicated equipment because it has many parts, not like a normal pressure vessel, and it has two interacting fluids working inside, and it should not be in touch. So in case there is some internal leak or external leak, you might have an impact on the plant, and it will be a major impact. Corrosion is one of the main threats of the heat exchanger's integrity, which might impact the lifetime of the exchanger so that it can be reduced significantly and it would not provide the function as how it should be intended. Maintaining the heat exchanger against the corrosion is not only from the operating condition. It can be started from the initial design stage when you can do the fluid allocation, material selection, the details of the design of the parts of the heat exchanger, and during the quality control of the fabrication and how you are doing the fabrication, and later also how you are operating this exchanger, how you are maintaining the operating parameters as how it should be, and how you are doing the maintenance, inspection, the frequency, the techniques, and how you are doing the interpretation of the results so that you are keeping an eye on the exchanger condition. As we said, from the very initial stage of the heat exchanger, you might need to think about how to avoid the corrosion in future of the exchanger. As you can see, when you are thinking about which fluid to be allocated in which site, from the initial stage of the thermal design of the exchanger, you need to think about where the corrosion can happen and how it can happen. So I need to think about allocating the corrosive media in tube side, not in shell side. Why? Because you can easier select more resistant material in the tubes compared to the shell. You can also have some chance of containing the leak if it happens within the media, so it will not be process safety incident. Yes, it might have another risk, and the mitigation you need to think about from the internal passing and leakage. And also, if you can think about which media to be there, like the general and good recommendation for putting the cooling water in tube side, not in shell side, because you know the tendency of the cooling water to cause sedimentations and under deposit corrosion, it will be higher in the shell side. This schematic shows the main damages which we can face in shell and tube heat exchanger with main focus on the tube side. As you can see, each location of the tube can be subjected to some specific types of attack. Whether it is stress corrosion cracking, and we'll see in separate slide the main factors and why we can think about it mainly in the tube-to-tube sheet joint, crevice corrosion and how to eliminate it because it might face in the tube sheet to the tube interface at the hole between them, and erosion corrosion, which mainly in the inlet of the tube, if it is there by any mean, galvanic corrosion based on the material selected either between the tube and the tube sheet or between the tube bundle and the baffle itself. Stress corrosion cracking and the location where you have higher stress, whether it is applied or mainly residual stress. So you need to think about the tube-to-tube sheet joint, whether stress relief is required, or if there is a U-bend and you need to do some stress relief, the expansion you are doing between the tube and the tube sheet so that to which extent of expansion you need to do based on the material selected. Many damage mechanisms can happen, many types of corrosion depend on service and in location. Understanding those points, as you can see, you need to tackle all of them, some mainly from the design perspective, early stage or during the fabrication, or later how I am maintaining the quality of the media inside to avoid such attack. The main factors affecting the corrosion which you can face. As we see in the previous slide, you can have different types of attacks: stress corrosion cracking, fatigue, corrosion fatigue, and all of those have some parameters need to be applied or exist at the same time so you can face this type of corrosion. For example, stress corrosion cracking, you need to have the three, the media, the material susceptible, and the stresses, whether it is residual or applied stresses. Those slides are mainly background, and then you can see in the next slides, which you also at the end will see some case histories reinforcing on what you are explaining right now, that especially in the heat exchangers, how you can mitigate or avoid such types of the general attacks. For example, the first one is the crevice corrosion, where we can see the crevice corrosion in the heat exchanger. In the location where you can have some trapped or localized area which you can see this issue, like between the tube and the tube sheet, mean this issue. Or if you have some vertical heat exchanger and the top part of the tube where there is some trapped media can cause deposits, and those deposits can have the tendency to have the corrosion or the crevice corrosion. If you think about the main area which focus mainly on the tube to tube sheet area, you can tackle this issue if you know from the beginning that it will have the crevice corrosion by design. So in some special cases, you need to think about setback weld or in-bore welding, so you are totally eliminating this type of crevice, and like what we see in some of the waste heat boiler, which is highly aggressive to cause crevice corrosion. Or simply by the initial step where you are allocating the fluid, so you need to allocate the fluid which have the tendency to crevice in tube side, not in shell side. And also again during the fabrication, how you are doing the expansion, and you will see one of the case histories, how the expansion during the fabrication was improperly, and it was the main cause for the attack to the crevice corrosion. One of the initial stages, very important stage, is the selection of the material. So if you know that the crevice cannot be avoided by design or by the fabrication, or you are doing your best, but still there is a chance, so you need to think about the material selection as well. You might step back again and change the material. You know that many of the materials have higher tendency to be attacked under crevice corrosion compared to their condition without crevice. This simple graph showed how the impact or how the tendency of some of the stainless steel grades, including austenitic stainless steel, duplex stainless steel, and the special high austenitic stainless steel alloys, between the normal pitting attack resistance to the crevice resistance. There is major difference between them. The material will have higher tendency to be attacked by crevice if it is there. So you might select the material suitable for the service, but because you have introduced the crevice and you didn't eliminate the crevice properly, this will be one of the factors impacting the lifetime of the equipment, of the heat exchanger. As we said in the beginning, selecting which fluid to be in which side, one of the most common cases is the cooling water. Cooling water, one of the normal media available in almost all the plants, because it's part of the utility itself. And there is very good recommendation in most of the standards right now to allocate the cooling water in the tube side, not in shell side. At the end, this is one of the recommendation. In some cases you cannot do. You need to put the cooling water in tube side, not in shell side. In shell side, not in tube side. Like very special cases of high pressure application where the high pressure side in shell side, not an economical choice. But you need to think about allocating the cooling water in tube side so that you can eliminate the tendency of the attack. And this issue can be from the very low velocity in the shell side, and also it can be from the localized high velocity if it can happen. And for the pitting corrosion, as we said earlier, the attack of the pitting can be also part from the design itself, the design detail. If you are providing a location like the one in the bottom left, as you can see, location where deposits can be accumulated and you can have an issue of the pitting attack. Same for the erosion corrosion or the flow erosion and the flow accelerated corrosion, which you need to think about not only from the material perspective, but also you need to think about the detail of the design to avoid such attacks in the tube, like what we can see from the ferrules inserted there. And the stress corrosion cracking, the location for the high localized stresses, especially if stress relief not applied at the U-bends, or the location where you are doing the expansion of the tube to the tube sheet. As you can see the figure here, if you are doing the expansion and the expansion extended to the edge of the tube with the tube sheet from the back side, from the shell side, you can create a very high localized area of stress concentration, which might be an area for attack later. And again, one of the main parts, if you are having this stress corrosion crackings, you need to think about the initial stage of the material selection to select the most suitable material. If it is a chloride, for example, and you cannot avoid the chloride at high temperature, so you need to think about a more resistant material, so you need to shift to the nickel-based alloys as recommended in the Cobson curve, the well-known one. And this, between the materials have stress corrosion cracking, many different materials can have this issue. Again, for the galvanic corrosion, it is part of the material selection and also can be somehow accommodated by localized weld overlay to protect it, or by painting so that you are eliminating the chloride from being contacted with the two different materials. Vibration is mainly part of the design. So again, from the initial stage, if you are not doing the design properly, you can have an issue. And during fabrication, if the tube bore in the hole, if the baffle itself is more than how it should be, so I are also increasing the tendency. So from fabrication, from the design, and also from operation if you are exceeding the normal operating parameters. And one of the main damage mechanisms can happen there, the hydrogen attacks, whether it is hydrogen embrittlement or high temperature hydrogen attack. You can see in the bottom section, the most famous failure happened in Tesoro in 2010 for the high temperature hydrogen attack for the heat exchanger, which was the cause for the update of EPI 941. One of the main is to protect the material from the hydrogen attack is the cladding weld overlay. But if you are doing this one, you need to think about the surface. Not every type of cladding or weld overlay are suitable for the hydrogen attack. Which one you need to do? Weld overlay, explosion bonding, or hot roll bonding. And if you are doing this one, you need to think about how it can impact the decreasing the diffusivity of the hydrogen. It will not be immune. You need to think about the thickness of the weld overlay which should be applied. And also during the, as you can see in the most bottom right over there, the note from ASME PCC2, that even during inspection, if you are doing hydro test in a material, chromium moly steel, and it was exposed to hydrogen, so you can put the material in risk by the inspection activity itself. And strain hardening, one of the most common issues with static stainless steel, if it's not stress relieved, you'll be subjected to this one. Selecting the material impact on the heat transfer is not that much impact, as you can see. Like 2% only from the heat transfer effect. And from the very initial stage of the design, selecting the joint design, which type of joint you are selecting, you need to understand that each of them has a strength, each of them has a weakness, so you need to think about the most suitable one for your service to avoid this attack. And that's what we said about the special type of tube-to-tube sheet weld to avoid the crevice. This is one of the most common recommendation in ASME for avoiding welding to the high stress area if you are using distribution belt, and we will see in the case history one of those cases that it is missed. And why it is missed? Because this is not one part of the design process, design procedure. So if you are using software, for example, for the design of the equipment, this will not be catch. This is by experience mainly, because it's not part of the normal process calculation. And the thread of the risk of the threaded plugs in the heat exchangers, which are still used in many exchangers while it's not really required. And in many cases, it is one of the impacting the plant to have a leak. Now coming to the case histories, which will enforce on what we will try to explain in the previous slides. This is one of the equipment which was fabricated, and after 16 years in service in one of the plants, you can see how it was failed. This part in the top right section, this is the channel of the exchanger. It was flied away, and the pipe was totally damaged. This is a big pipe, by the way. And what happened? It's supposed to be P11 material, 1/4 chrome, because it is in hydrogen service, high temperature hydrogen attack. And during fabrication, by mistake, carbon steel material was used. Just imagine such a fabrication issue. It can withstand 16 years, and it was passed until you have a failure. So it is a part of the quality control. And that's what we said about you can have some note in the code, for example, if you missed it, like welding here the impingement plate or the distribution plate inside the vapor belt to the high stressed area. This equipment, after 1 year in service, only start to be cracked. And this is related to allocating the cooling water in the shell side. As you can see how the cooling water in the shell side after some time can impact the shell side by high deposition rate and under deposit corrosion, impacting the lifetime of the heat exchanger. Another case for the stress corrosion cracking. You can see here the cause was stress corrosion cracking in the tube-to-tube sheet joint, and it was improper expanding of the tube-to-tube sheet, and this improper expansion allowed for the crevice from the backside of the shell, impacting the weld and causing stress corrosion cracking of this equipment. That was our last case history, and thank you for your time. If you have any question, and excuse me if I exceeded by 1 minute or so.